Welcome to the PowerPoint show here. We're going to be looking at patterns and sequences, and it is very important and key to being able to teach students to look at patterns or sequences and determine what might come next. Sometimes patterns, being able to look at patterns, we call it the art of problem solving. And a lot of things are involved, a lot of problem-solving skills in looking at patterns. Two of them are being able to compare and contrast. So you compare to find the parts or the elements that remain constant, and you contrast to find those that are changing. And here's just a quote that there are many different forms of patterns. So let's look at some. So often we'll have some examples where we're given a pattern and we want to know what should come next and why. So here's one pattern. Then we have another one. This one is not made of letters, but it's made up of figures. And then another pattern where we might want to see what comes next is this pattern of numbers. So if we look at these, we can see that things are kind of being repeated. So we want to look for what the core is, where these repeat. So we want the same exact thing repeated. Now notice here, I have 1. I have 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Starting again with 1. So this would be my core. I start with 2 squares, so that's going to be for this one. Start with 2 squares. So each pattern should start with the 2 squares, and then followed by a smiley face and a heart and one more square. 2 squares, smiley face, heart, and 2 more squares, and so forth. So this would be the core here. What do you think would be the core here? Well, if you guessed ABA, 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 you're correct. So what should come next? I should repeat the core again here. Repeat the core again here. Star, square, smiley face, heart, another square. And again, this would repeat. I've got the 1 started, 4, 6, 4, 1, and so forth. Okay, let's look at a few other patterns. Here's one. Here's another. And here's a third. Now, if I look here, I may not see a core that repeats itself. 1, 3, 2, 1, 3, 1, 3, 2, 1. So the core here may not be obvious, or I may not even see a core. But these ones do have a core, but the core does not remain the same. It grows. So if I look here, I have A's, single A's each time. Then I have 1B, 2B, 3B. So it looks like the core is growing by adding an extra B each time. So I would have A, B, 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 B would be the next one. Here, let's see how this core might be growing. 3, 5, 1, 3, 5, 5, 1, 3, 5, 5, 5, 1. So the growth is occurring with the 5s. So each time I repeat, the 3 and the 1 stay in the relatively same place, but the 5, we increase the number of 5s that we have. So now we would have 3 4 5s and a 1. Here we have 1 3 2, 1 3, 1 3, 2, 1 3, 1 3, 1 3, 2. So it looks like it's this 1 3 that is increasing in number each time. The 2 remains constant. Here I have 2 1 3s and a 2. 3 1 3s and a 2. So the next one would have 4 1 3s and a 2. So one of the patterns we see in nature is the way things grow or multiply. And Fibonacci was a mathematician who came up with this famous pattern by looking at rabbits multiplying. Now what we have to remember is that a baby rabbit cannot multiply when it's first born. It has to be a month old before it can start multiplying. So if we look at the first month, we've got 1 pair of rabbits. In the second month, we've got the same pair of rabbits that have grown up. And in the third month, this pair of rabbits have had a baby, had a pair of babies. So we got 2 pairs of rabbits. This pair, the adult pair we started with, can have another baby, and the babies can grow up. So now we have 3 pairs of rabbits. Now rabbits live for a while, so that same adult pair of rabbits is having a pair of babies. This pair of rabbits has grown up. This pair of rabbits has had a pair of rabbits. So now we have 5 pairs. So if I wanted to look at these numbers, I start out with some number. Okay, then I'm going to repeat that. And then if I add those 2 numbers together, I get 2. And if I add these 2 numbers together, I'm going to get 3. And if I add these 2 numbers together, I'm going to get 5. And then I can repeat this. So depending on what you start out with, you can start a Fibonacci sequence with different numbers. But this is the basic one we first look at. And then we also have a pattern named after Blaise Pascal, another mathematician. In fact, he's probably considered the father of computing. So if we look at a row and then start making successive rows, so we'll start with 1, then we bring the 1 down on each corner. And then again, we bring the 1 down on each corner, but now we add those 2 to get what's in the middle. So here, I'll bring down the 1, add these 2 to get 3, add these 2 to get 3, and bring down the 1 again. And I continue that pattern. And this is known as Pascal's triangle. So add 1 and 3, I get 4. 3 and 3, I get 6. 3 and 1, I get 4. And then bring the 1 down. So I'm making sort of a pyramid of numbers. Now, you can make a similar triangle starting with different numbers on the row. But this is the basic pattern you're looking at. Then we have what's called arithmetic sequences. Okay, they're arithmetic because each pair, if I look at the difference between the numbers is the same difference. So if I look at 8 minus 5, I get 3. The difference between 8 and 11 is also 3. 11 and 14 is 3. 14 and 7 is 3. So the next one should be 3. So my next number should be 20. And so forth. So we call the 3 the common difference. 20 is the number that comes next. Why? Because if I add 3 to 17, I get 20. Okay, so arithmetic sequences have a core, have a definite pattern, but they don't have a core that repeats or grows. They just have common differences. Okay, so the pattern is in the difference, not in the core. So, if I want to think about the connection between arithmetic sequences and how they relate to how I might express the terms in algebra, we're going to find an algebraic rule. So here's our arithmetic sequence we started out, okay? And we know that the common difference here is what? 2 and 7, the common difference is 5, 5, 5, 5. So the next number and should be 27. So this is the term. So the first term is 2, the second term is 7, the third term is 12. So what I want to know is what happens when I get to any general term, an arbitrary term n. How can I know what that is? Okay, so the position, again, is referred to as the term. Now the initial term is 2. Okay. So what we do is we find the common difference, multiply the difference by n minus 1, where n is the term, and then we add that to the initial term. So we have this n minus 1 because for my first term, I want to get 2. So if I put 1 in for the number here, that's going to give me 0. So what I would find is that x sub 1 is equal to 2 plus 5 times 1 minus 1, which is 0. The 5 times 1 minus 1, which just gives me 2. Okay? Then I could do the same thing with the second term, which would be x sub 2. 2 plus 5 times 2 minus 1, which would be 2 plus 5 times 1, which is 7, which is my second term. But now remember, we can simplify this by distributing the 5 here. So x sub n equals 2 plus 5n minus 5, 5n minus 5. We can combine the 2 and the negative 5, and we end up with 5n minus 3. We also have a different case when we have common ratios. Okay, so in this case, a number is not added each time. We use a common multiplier each time. And this is called the common ratio. And what we get is a geometric sequence. So if I look here, 5 divided by 1 is 5. 25 divided by 5 is 5. And each time I do the division, I'm going to get 5. So that's called my common ratio. Now the common ratio does not have to be a whole number. It might be a fraction. that you're multiplying by each time. But it's still called a common ratio. Okay, so now if we want to find an algebraic rule, okay, what we do is we first find the common ratio, and whatever, this ratio is, we raise it to the n minus 1 power, and then multiply that by the initial term. Well, here we had a common ratio of 5, and our initial term is 1. So we're multiplying by, and if you think about it, I'm taking the first number and multiplying it by a 5, and then I'm going to multiply by another 5, and another 5, and another 5, so forth. So if I want to find the first term, my n here is 1, so that's 1 minus 1. Whoops. Which is 1 times 5 to the 1 minus 1 is 0. And anything raised to the 0 power, except for 0 itself, is 1. So this turns out to be 1. So if I wanted to find, say, the fourth term, I use my initial term. 5 is my common ratio. I'm doing 4 is my n here, minus 1, which turns out to be 1 times 5 cubed, which is 125. And then we also have types of sequences that are not arithmetic and not geometric. Okay, they don't necessarily have a core that repeats. We could kind of think of it as a core that grows, but they form different figures. So we call these figurate numbers. So the triangular numbers, if I take a 1 dot and start with that and make the next triangle with 3, okay, and I add on another side by adding 3 more, and then here I add on another side on the bottom by having 4. And here I add on another side to that. Now I have 5 as the base. So you can think of it adding a base, or you can think of it as adding a side. Either way. But the idea is that the numbers themselves, if you use that number of dots, you can make a consistent kind of shape. So this is one kind of link between geometry and arithmetic. And then we have sequences where we might be able to find finite differences. Okay, so if I find the initial difference between here, so 0, 3, the difference is 3, 3 and 8, the difference is 5. Okay, I don't have a common difference here. Okay, but if I look at the next step, 3 and 5 has a common difference of 2. 5 and 7 has a common difference of 2. Common difference of 2. Common difference. Now I know what I'm working with. So if I look at 9 and add the 2, then I get 11. So if I wanted to find the next number here, add the 24 and the 11 and get 35. So these have finite differences, which means eventually the difference will become the same. It may not be the first step, may not be the second step, but it will be some step. You don't have to go forever. Now, we use these patterns as examples of inductive reasoning. Inductive reasoning basically is reasoning by patterns, looking for patterns to see if there is one, and then you can draw a conclusion. So you're looking at specific examples to draw a conclusion. If you want to disprove inductive reasoning. If it's false, all you have to do is come up with an example where it doesn't happen. And that is called a counterexample.